In this presentation, we shall learn according to the new WBSCTE syllabus for Applied Physics for Semester 1, Unit 6 about heat and thermometry. Here we shall cover Unit 6.2 where we have expansion of solids, liquids and gas, coefficients of linear, surface and cubical expansion of solids and relation amongst them, specific heat Cp and Cv of gas and their relation. Here, the students will be able to Number 1. State the thermal expansion of solids, liquids and gases with examples. Number 2. Obtain the coefficients of linear, surface and cubical expansions of solids. Number 3. Derive relation amongst these coefficients. Number 4. Explain specific heat Cp and Cv of gas. Number 5. Write the relation between Cp and Cv of a gas. And number 6. Solve simple numerical problems. Slide 3. Thermal expansion of solids. Solids expand on heating. As the animation shows, according to kinetic theory, the vibrating atoms of solids on heating vibrate with more kinetic energy and amplitude. This requires more space and so the substance expands. For example, railway lines provide with gaps to accommodate for the expansion. Number 2. In bimetallic strip, invar and brass have different expansions. Like solids, liquids also expand on heating. We can see from the animation that on heating, the random motion of the liquid molecules increases. To accommodate space for increased vibration, the volume increases. Here, the expansion of the container is to be considered. The coefficient of real expansion of liquid is equal to the coefficient of the apparent expansion of liquid plus the coefficient of the volume expansion of the container. Gases also expand on heating. Gas needs a closed container. More space is required to accommodate for the increased vibration. Consider a cylinder fitted with a piston which contains some gas. When heated, the gas expands, which is noted from the moving of the piston. Example, the piston of a cylinder of a car engine expands due to the expansion of the fuel vapor. Coefficient of thermal expansion of solids. Here we talk about the coefficient of linear thermal expansion. A solid of length L1 at theta 1 degree Celsius increases to L2 when heated to theta 2 degree Celsius. Here the change in length is delta L, that is equal to L2 minus L1. It is found that delta L is proportional to L1 and delta L is proportional to theta 2 minus theta 1. So combining we get delta L is equal to alpha into L1 into theta 2 minus theta 1, where the coefficient of linear expansion alpha is equal to L2 minus L1 by L1 into theta 2 minus theta 1, that is L2 is equal to L1 into 1 plus alpha into theta 2 minus theta 1. Similarly, if a solid of length L0 at 0 degrees Celsius increases to L1 when heated to T degrees Celsius, then we have alpha equal to LT minus L0 by L0T, that is LT is equal to L0 into 1 plus alpha T. The unit of the coefficient of linear thermal expansion is per degree Celsius in CGS or per Kelvin in SI. The list of coefficients of linear thermal expansion is shown in the table on the right side. For coefficient of surface expansion deriving in the same way as in the linear expansion, we obtain beta is equal to A2 minus A1 by A1 into theta 2 minus theta 1, and A2 is equal to A1 into 1 plus beta into theta 2 minus theta 1. For volume or cubical expansion, the derivation is shown in the same way, and we obtain that gamma is equal to V2 minus V1 by V1 into theta 2 minus theta 1, and V2 is equal to V1 into 1 plus gamma theta 2 minus theta 1. We can relate the three coefficients of expansion, that is alpha, beta and gamma. Let us consider a rectangular plate with length A and breadth B at certain temperature. Its area is A1 equal to A into B. If the temperature is increased by theta and the length will be A into 1 plus alpha theta and breadth will be B into 1 plus alpha theta, A being the coefficient of linear expansion. So the increased area A2 is equal to A into B into 1 plus alpha theta whole square. So approximating, we get AB into 1 plus 2 alpha theta. So that is A1 into 1 plus 2 alpha theta, as AB is A1. So by definition of the surface expansion, we have A2 is equal to A1 into 1 plus beta theta. So by comparing these two equations, we have beta equal to 2 alpha. A cube of length L has surface area A equal to L square. The coefficient of linear expansion is alpha equal to 1 by L into dl d theta. Now differentiating with respect to theta, we get dA d theta is equal to 2L dl d theta. The coefficient of surface expansion is beta equal to 1 by A dA by d theta equal to 2 1 by L dl by d theta, that is equal to 2 alpha. Let us consider a rectangular block with length, breadth and height A, B and C respectively at certain temperature. So its volume is V1 equal to A into B into C. If the temperature is increased by theta, the length, breadth and height will be A into 1 plus alpha theta, B into 1 plus alpha theta and C into 1 plus alpha theta respectively, alpha being the coefficient of linear expansion. The increased volume, that is V2, is equal to A into B into C into 1 plus alpha theta whole cube. By simplifying, we have ABC into 1 plus 3 alpha theta. So we have V2 equal to V1 into 1 plus 3 alpha theta. By definition of surface expansion, we have V2 is equal to V1 into 1 plus gamma theta. Now comparing these two equations, we have gamma equal to 3 alpha. A cube of length L has a volume of V equal to L cube. The coefficient of linear expansion is alpha equal to 1 by L dl by d theta. Differentiating with respect to theta, we have dV by d theta equal to 3L square dl by d theta. The coefficient of volume expansion is gamma equal to 1 by V dV d theta, that is equal to 3 into 1 by L dl by d theta, that is equal to 3 alpha. The specific heat capacity or simple specific heat of a substance is the heat energy required to raise the temperature of a unit mass of substance through unit temperature. When a unit mass of gas is compressed, suddenly its temperature rises but no heat is supplied. That is C equal to delta Q by delta T equal to 0 by delta T, that is equal to 0. Also, during sudden expansion of the gas, if we apply a specific amount of heat, the temperature remains same. So C equal to delta Q by delta T equal to delta Q by 0, that is becomes infinite. So this is an absurd situation that says that the mass of the gas can have any value of specific heat. So in definition on the specific heat of solids and liquids, we have not considered the change in the volume with pressure, as it is negligible. In case of gas, the change in the volume is to be considered. So gases are supposed to have two specific heats, specific heat at constant volume Cv and specific heat at constant pressure Cp. Definition of specific heats. Specific heat at constant volume, that is Cv, of a gas is the quantity of heat required to raise 1 gram of the gas through 1 degree Celsius, keeping its volume constant. In CGS, the unit is calorie per gram per degree Celsius. Specific heat at constant pressure Cp of a gas is the quantity of heat required to raise 1 gram of the gas through 1 degree Celsius, keeping its pressure constant. Its CGS unit is calorie per gram per degree Celsius. Now, molar specific heat, that is the m being the molecular weight of the gas, it is the specific heat for 1 mole of gas. In SI, the unit is joule per mole per Kelvin. Here, capital CV is equal to capital M into small cv and capital Cp equal to capital M into small cp. Reason for Cp greater than Cv. At constant pressure, the heat supplied to a unit mass of gas is equal to the internal energy rise, showing temperature rise plus work done due to the volume change. The heat supplied to a unit mass of a gas at constant volume is equal to the internal energy rise, showing the temperature rise. So, greater heat is required by unit mass of gas at constant pressure to have equal temperature rise than that at the constant volume. Molar specific heats are related by the relation number 1 Cp minus Cv equal to capital R, where capital R is equal to 8.315 joule per mole per Kelvin is the molar gas constant. To obtain the relation for 1 gram of the gas, divide throughout by the molecular mass of the gas, that is capital M. Number 2, Cp by Cv is equal to gamma, where gamma is the adiabatic gas constant. Thank you.